Hello, today we're going to look at vectors. So again, because we're in chapter 10 here, we're going to look primarily at 3D, but we'll also look at them in 2D a little bit. In a mathematical sense, we can extend these vectors to be any size, but if we're thinking geometrically, we're really going to just have 2 and 3D vectors. Okay, so let's go ahead and look. Okay, so very first, our definition. So a vector is simply a directed line segment. Okay, it has to have a direction and a place, and well, that's about it, really. Here we have 2 points in space, wherever they might be, again, 2D or 3D. We can denote the vector from P to Q as PQ. And then you'll see we have this arrow over the top. That'll indicate to us that we're talking about a vector. I'm going to stick to that notation. You might see different notation in other places. In some places, it's bolded to indicate a vector. Occasionally you'll see it with a line written underneath it to indicate it's a vector, even a line above it that isn't an arrow. But I'll say I'm going to stick to this notation, so when we see something with the arrow above it, we'll know that that's a vector. Okay, and we can refer within this vector to P as the initial point and Q as the terminal point where we end. Okay, so here's just a couple of simple examples, again in 2D and then 3D. So our vector A goes 1 in the x direction and -2 in the y direction. And you'll see we have those kind of angled brackets to indicate we have a vector as well. And then B is now in 3D. So B goes 0 with a -3 and then 7, again with the angled brackets. So that's how we'll indicate we have a vector there. One more thing to mention, the magnitude of a vector is denoted with these 2 parallel lines on either side. So we have a vector in there, we have its magnitude. So we can think about this as actually just the length of the vector. And occasionally you'll hear it referred to as the norm. We'll probably stick to magnitude, but it really is just the length in terms of 2 or 3D points. Again, if we go more than 3D, maybe it doesn't make sense to think about it as a length, and we would use magnitude there. Okay, so that's denoted as, say, like so. So if we have some vector A, which is 3, 4, and we want to find the magnitude of A, well, again, the Pythagorean theorem just comes in very handy for us there. So it's the square root of 3 squared plus 4 squared, which of course is square root of 25, which is 5. As mentioned, we don't have to stick to 2D, we can go to 3D. So if B is now this vector in R3, -2, 5, 8. Again, to find the magnitude of that, we'll simply take each of the values, square them, add them all together, and take the square root. And so that's 9.64. Okay, so nothing particularly hard or difficult there. Again, summing. Summing is pretty straightforward. So we have 2 vectors, A, B, and C, D. And to sum them, then we just sum the elements in the corresponding positions. So the first position gets A plus C, and the second position gets B plus D. So graphically, here's what this looks like. I think it's easier to think about going along here. So we go up along U, and then we add V. So we go U, we put the start of V at the end of U, and then go along V, and that creates a new vector, which is UV, U plus V, which goes all the way up here. Because addition, it doesn't matter which order you do it in, it's commutative. We could also do it this way around, but I think it's more natural to think about going along U and then V. So there it is graphically, and then of course if we just actually calculate it, U here is 1, 3, V is 2, 1. So we add them together, we get 3, 4, and that's exactly what the graph shows. Subtracting, well, it's all exactly the same thing. If we subtract, we just subtract in each of their pieces. Here I think, so we're taking U minus V, I think it's easy to think about. We go along U, and then we come back down V. Right, V's natural direction is to go right and up. So if we take -V, we go kind of left and down. And so when we subtract that, we get U minus V, which comes along here. Okay, so that's U minus V. And again, we can do the very simple math. Take 3 minus 1 and 1 minus 2 to get 2, -1. And again, that's exactly what the graph shows. Now, multiplying vectors. So we have to be a little bit careful when we talk about multiplying vectors. In the next week or so, we'll look at dot products and cross products, which we can kind of think of as a way of multiplying vectors. but we can't directly multiply vectors in the way we might think. What we can do is multiply a vector by a scalar. In other words, just multiply it by a number. So we have the vector u and the number c. Then to find cu, we just take each element within u and multiply it by c. So if u is ab, then cu is ca and cb. So just taking that very simple example there, if we have 2 times by 2, 1, we just multiply the 2 by 2 and multiply the 1 by 2. And graphically what this looks like, basically that vector v would just go along it twice the distance. Okay, so doubling 2, 1 is 4, 2. But I say we have to be a bit careful. We're not saying we're multiplying a vector by another vector. We're multiplying a vector by a scalar. Okay, so we have a whole bunch of properties here. I think most of these are fairly straightforward and nothing will surprise you. They act most ways are like regular addition. So number 1 there is the commutative property, which says it doesn't matter in which order we add u and v. And then 2 is the associative property, which says, well, we have u and v and w. We really can just write u plus v plus w. It doesn't matter whether we do the u plus v first or the v plus w first. The additive identity, so we can have the 0 vector. So the 0 vector is just 0, 0, 0. Or I guess just 0, 0 if you're in 2D. And if you add that to a vector, it leaves it unchanged. 4 just talks about multiplying by scalars. Again, it doesn't matter. And then 5 and 6 talk about distributing. So we can distribute a scalar over u and v, or we can distribute those 2 scalars, c and d, over v. If we multiply a vector by the scalar 0, we get the vector 0. That's number 7. So 0 times by 1, 2, 3 is just 0, 0, 0. If we multiply a vector by a constant c, and then we take the magnitude, well, it's just the same as multiplying by c. With being slightly careful, you can see we have the absolute value of c there, just in case c is negative. And finally, the only way a vector can have a magnitude of 0 is if it is itself 0. Okay, so the 0 vector has a magnitude of 0, but nothing else will. Everything else will have a positive magnitude. Okay, so we've raced through those, but I think they're fairly straightforward. Unit vectors are an important thing. So unit vector is a vector with a magnitude of 1, which obviously we can denote with this notation. So the magnitude of v is 1. But if we have any other vector, we can transform it into a unit vector, I guess except for the 0 vector, by just simply dividing by that magnitude. So its magnitude is 7. If we divide that magnitude by, or divide the vector by 7, its new magnitude would be 1. And so, for example, if we had the vector 1, 2, 3, and we want a unit vector in that same direction, so it's in the same direction as v, but just has length 1, we just divide that vector by its magnitude, in this case root 14, and so we get 1 over root 14 times by the original vector. You can distribute that 1 over root 14, but I'm not sure there's any need to. If anything, I think it makes it look a bit messier, to be honest. Okay, so we get 1 over root 14 times by 1, 2, 3, and let's say that's a vector in the same direction as 1, 2, 3, but of length 1. Within both R2 and R3, we have what are called standard unit vectors. So R2, right? And actually, yeah, let's just briefly talk about that notation. R2, so obviously the 2 means it's a vector of length 2, and the R really is saying to us that the elements of it can be any real number. Okay, we'll obviously mostly deal with integers, but they could be any real number in there. So in R2 of length 2, the I is 1, 0, and the j is 0, 1. Those are the standard unit vectors in R2. So you can think about the I going along 1 unit along the x-axis, the j going 1 unit up on the y-axis. And then similarly in R3, we have the standard unit vectors. So we have I, j, and k now. I is 1, 0, 0, j is 0, 1, 0, k is 0, 0, 1. Okay, and we can use those vectors. So for example, if we see the vector 3, 4, 7, here's another way we can write that. It's 3 in the I direction, 4 in the j direction, and negative 7 in the k direction. So 3i plus 4j minus 7k is the same as the vector 3, 4, 7. So this is just a different notation. It's useful on certain occasions, but there's nothing too tricky about that. Okay, so that's all we have on vectors for today. Thank you.